This is another reason I like doing things like APL study groups, because it's a way of like self-selecting that small group of humanity who's actually interested in trying new things, despite the fact that they're grown-ups, and then try to surround myself with those people in my life.
Welcome to another episode of ArrayCast. I'm your host, Connor, and today we have a very exciting guest, which we will introduce in a second. But before we do that, we'll do brief introductions and then one announcement. So first we'll go to Bob, and then we'll go to Adam, who has the one announcement, and then we will introduce our guest.
I'm Bob Terrio. I'm a J enthusiast, and I do some work with the J Wiki. We're underway in trying to get it all set up for the fall.
I'm Adam Bolzewski, full-time APL programmer at Dyalog Limited. Besides for actually programming APL, I also take care of all kinds of social things, including the APL Wiki. And then for my announcements, part of what we do at Dyalog is arrange a yearly user meeting or a type of conference. And at that user meeting, there is also a presentation by the winner of the APL problem solving competition. That competition closes at the end of the month. So hurry up if you want to participate. It's not too late even to get started at this point. And also at the end of the month is the end of the early bird discount for the user meeting itself.
Awesome. And just a note about that contest, I think, and Adam can correct me if I'm wrong, there's 2 phases. In the first phase, it's just 10 short problems. A lot of them are just one-liners. And even if you only solve one of the 10, I think you can win a small cash prize just from answering one. Is that correct?
I'm not even sure. You might need to solve them all, but they're really easy.
Okay. So the point being, though, is that you don't need to complete the whole contest in order to be eligible to win prizes.
No, for sure.
There's a certain amount that if you get to that point, you hit a certain threshold, and you can be eligible to win some free money, which is always awesome. And yeah, just briefly, as I introduce myself in every other episode, I'm your host, Connor, C++ professional developer. Not an array language developer in my day-to-day, but a huge array language and combinator enthusiast at large, which brings us to introducing our guest, who is Jeremy Howard, who has a very, very, very long career, and you probably have heard him on other podcasts or have given other talks. I'll read the first paragraph of his 3-paragraph bio because I don't want to embarrass him too much, but he has a very accomplished career. So Jeremy Howard is a data scientist, researcher, developer, educator, and entrepreneur. He is the founding researcher at Fast.ai, a research institute dedicated to making deep learning more accessible, and is an honorary professor at the University of Queensland. That's in Australia, I believe. Previously, Jeremy was a distinguished research scientist at the University of San Francisco, where he was the founding chair of the Wicklow Artificial Intelligence in Medical Research Initiative. He's also been the CEO of Enlitic and was the president and chief scientist of Kaggle, which is the basically data science version of LeetCode, which many software developers are familiar with. He was the CEO of 2 successful Australian startups, Fastmail and Optimal Decisions Group. And before that, in between doing a bunch of other things, he worked in management consulting at McKinsey, which is an incredibly interesting start to the career that he has had now, because for those of you that don't know, McKinsey is one of the 3 biggest management consulting firms alongside, I think, Bain & Co. and BCG. So I'm super interested to hear how he started in management consulting and ended up, being the author of one of the most popular AI libraries in Python, and also the course that's attached to it, which I think is, if not, the most popular, a very, very popular course that students all around the world are taking. So I will stop there, throw it over to Jeremy, and he can fill in all the gaps that he wants. Jump back to however far you want to tell us, how you got to where you are now. And I think the one thing I forgot to mention too is that he recently tweeted on July 1st, and we're recording this on July 4th, that he quote, the tweet reads, "Next week, I'm starting a daily study group on my most loved programming language, APL." And so obviously interested to hear more about that tweet and what's going to be happening with that study group. So over to you, Jeremy.
Well, the study group is starting today as we record this. So depending on how long it takes to get this out, it'll have just started. And so definitely time for people to join in. So I'm sure we'll include a link to that in the show notes. Yeah, I definitely feel kind of like I'm, your least qualified array programming person ever interviewed on this show. I love APL and J, but I've done very, very little with them, particularly APL. I've done a little bit with J, mucking around, but like I find a couple of weeks here and there every few years, and I have for a couple of decades. Having said that, I am a huge enthusiast of array programming as it is used, in a loopless style in other languages, additionally in Perl and nowadays in Python. But yeah, maybe I'll come back to that because I guess you wanted to get a sense of my background. Yeah, so I actually started at McKinsey. I grew up in Melbourne, Australia, and I didn't know what I wanted to do when I grew up at the point that you're meant to know when you choose a university, major. So I picked philosophy on the basis that it was like, the best way of punting down the road what you might do, because with philosophy you can't do anything. And honestly, that kind of worked out in that I needed money, and I needed money to get through university. So I got a 1 day a week kind of IT support job at McKinsey, the McKinsey Melbourne office, during university from first year. I think that's from first year. But it turned out that I was very curious. And so I was very curious about management consulting. So every time consultants would come down and ask me to clean out the sticky Coke they spilt in their keyboard or whatever, I would always ask them what they were working on and ask them to show me. And I'd been really interested in doing analytics-y kind of things for a few years at that point. So during high school, basically every holidays, I kind of worked on stuff with spreadsheets or Microsoft Access or whatever. So it turned out I knew more about stuff like Microsoft Excel than they did. So within about 2 months of me starting this 1 day a week job, I was working 90-hour weeks, basically doing analytical work for the consultants. And so that actually worked out really well because I kind of did a deal with them where they gave me a full-time office and they would pay me $50 an hour for whatever time I needed. And so suddenly I was actually making a lot of money, working 90 hours a week. And yeah, and it was great because then I would come up with these solutions to things they're doing in the projects, and I'd have to present it to the client. So next thing I knew, I was basically on the client side all the time. So I ended up actually not going to any lectures at university. And I somehow kind of managed this thing where I would take 2 weeks off before each exam, go and talk to all my lecturers and say, hey, I was meant to be in your university course. I know you didn't see me, but I was kind of busy. Can you tell me what I was meant to have done? And then I would do it. And so I kind of scraped by a BA in philosophy, but I don't really have much of an academic background. But that did give me a great background in applying stuff like linear regression and logistic regression and linear programming and, the basic analytical tools of the day, generally through VBA scripts in Excel or, Access, the kind of stuff that a consultant could chuck out, onto their laptop at a client site. Anyway, I always felt guilty about doing that because it just seemed like this ridiculously nerdy thing to be doing when I was surrounded by all these very important, consultant types who seemed to be doing much more impressive strategy work. So I tried to get away from that as quickly as I could because I didn't want to be the nerd in the company. And yeah, so I ended up spending the next 10 years basically doing strategy consulting. But throughout that time, I did, because I didn't have the same background that they did, the expertise they did, the MBA they did, I had to solve things using data and analytically intensive approaches. So although in theory I was a strategy management consultant and I was working on problems like, how do we fix the rice industry in Australia? Or, how do we, how do we deal with this new competitor coming into this industry or whatever. I always did it by analyzing data, which actually turned out to be a good niche, because I was the one McKinsey consultant in Australia who did things that way. And so I was successful, and I became, I ended up moving to AT Kearney, which is the other of the two original management consulting firms. I think I became like their youngest manager in the world, and, through this weird parallel path I was doing. And then through that, learned about the insurance industry and discovered like the whole insurance industry was basically pricing things in a really dumb way. I developed this approach based on optimization of optimized pricing. And I launched a company with my university friend who had a PhD in operations research. And yeah, so we built this new approach to pricing insurance, it was kind of fun. I mean, it's, it went well in the set, commercially. Spent about 10 years doing that, and at the same time running an email company called Fastmail, which also went well. We started out basically using C++, and I would say that was kind of the start of my array programming journey, in that in those days, this is like 1999, the very first expression templates-based approaches to C++ numeric programming were appearing. And so I, was talking to the people working on those libraries, doing stuff like, particularly stuff doing the big kind of high energy physics experiments that were going on in Europe. It was ultimately pretty annoying to work with, though, like the amount of time it took to compile those things. It would take hours, and it was quirky as all hell. It's still pretty quirky doing metaprogramming in C++, but in those days it was just a nightmare. Every compiler was different. So I ended up switching to C# shortly after that came out, and move in a way. It was disappointing because that was much less expressive as a kind of array programming paradigm. And so instead I ended up basically grabbing Intel's MKL library, which is basically a BLAS on steroids, if you like, and writing my own C# wrapper to give me, kind of array programming-ish capabilities, but not with any of the features one would come to expect from a real array programming language around kind of dealing with rank sensibly and, not much in the way of broadcasting. Which reminds me, we should come back to talking about BLAS at some stage, because a lot of the reasons that most languages are so disappointing at array programming is because of our reliance on BLAS, as an industry. Fastmail, on the other hand, is being written in Perl, which I really enjoyed as a programming language, and still do. I still love Perl a lot. But the scientific programming in Perl, I didn't love at all. And so at the time, Perl 6, was just starting to, the idea of it was being developed. So I ended up running the Perl 6 working group to add scientific programming capabilities, or kind of, and at the time I described them as APL inspired programming capabilities to Perl. And so I did an RFC around what we ended up calling hyperoperators, which is basically the idea that any operator can operate on arrays and can broadcast over any axes that are mismatched or whatever. And those RFCs all ended up getting accepted, and Damien Conway and Larry Wall kind of expanded them a little bit. Perl 6 never exactly happened. It ended up becoming a language called Raku. And that, and the kind of the performance ideas I really worked hard on never really happened either. So that was a bit of that was all a bit of a failure. But it was fun and it was interesting. So after running these companies for 10 years, one of the big problems with running a company is that you're surrounded by people who you hired, and they, have to make you like them if they want to get promoted and not get fired. And so you could never trust anything anybody says. So I was, very I had very low expectations about my capabilities analytically because I hadn't I'd basically been running companies for 10 years. I did a lot of coding and stuff, but it was in our own little world. And so after I sold those companies, one of the things I decided to do was to try actually to become more competent. I had lost my to some extent, I had lost my feeling that I should hide my nerdiness, and try to act like a real business person. And I thought, no, I should actually see if I'm actually any good at this stuff. So I tried entering a machine learning competition at a new company that had just been launched called Kaggle, with this goal of not coming last. So basically, the way these things work is you have to make predictions on a data set, and at the end of the competition, whoever's predictions are the most accurate wins the prize. And so my goal was, try not to come last, which I wasn't convinced I'd be able to achieve because, as I say, I didn't feel like I'd never had any technical training, and everybody else in these competitions were PhDs and professors and whatever else. So it felt like a high bar. Anyway, I ended up winning it.
Oh, wow.
And that changed my life, right? Because, it was like, oh, okay, I am, empirically good at this thing. And people at my local R user groups, we used R quite a bit as well. I told them, I'm going to try entering this competition. Anyone want to create a team with me? I want to learn to use R properly. And I kind of went back to the next user group meeting, and people were like, I thought you were just learning this thing. How did you win? It's like, I don't know. I just used common sense. So I ended up becoming the chief scientist and president of Kaggle. And Kaggle, as anybody in the data science world knows, has kind of grown into this huge thing. Ended up selling it to Google. So I ended up being an equal partner in the company. I was the first investor in it. And that was great. That was I just dove in. We moved to San Francisco for 10 years, surrounded by all these people who I just thought of role models and idols. And partly getting to meet all these people in San Francisco was this experience of realizing all these people were actually totally normal, and they weren't some super genius level. They're just normal people who, as I got to know them, it gave me, I guess, a lot more confidence in myself as well. So
maybe they were just normal relative to you.
I mean, I think in Australia, we all feel a bit, intimidated by the rest of the world in some ways. We're a long way away, our only neighbours really are New Zealand. It's very easy to feel, I don't know, we're not very confident of our capabilities over here, other than in sport, perhaps. So one of the things that happened while I was at Kaggle was I had played around with neural networks a good bit, 20 years earlier. And I always felt like neural networks were one day going to be the thing. It's they are on a theoretical level infinitely capable, but they never quite did it for me. And but then in 2012, suddenly neural networks started achieving superhuman performance for the first time on really challenging problems like recognizing traffic signs, like recognizing pictures. And I'd always said to myself, I was going to watch for this moment. And when it happened, I wanted to jump on it. So as soon as I saw that, I tried to jump on it. So I started a new company after a year of research into what a neural network's going to do. I decided medicine was going to be huge. I knew nothing about medicine. And I started a medicine company to see what we could do with deep learning in medicine. So that was Enlitic. That ended up going pretty well. And eventually I kind of got like a bit frustrated with that though, because it felt like deep learning can do so many things, and I'm only doing such a small part of those things. So deep learning is like neural networks with multiple layers. I thought the only way to actually help people really, make the most of this incredibly valuable technology is to teach other people how to do it and to help other people to do it. So my wife and I ended up starting a new, I'd call it kind of a research lab, Fast.ai, to help do that. Basically, initially focus on education, and then increasingly focus on research and software development to basically make it easier for folks to use deep learning. And that's where I am now. And that everything in deep learning is all Python. And in Python, we're very lucky to have excellent libraries that behave pretty consistently with each other, basically based around this Numpy library, which treats arrays very, very similarly to how J does, except rather than leading axis, it's trailing axis. But basically, you get you get loop free, you get broadcasting. You don't get things like a rank conjunction, but there's very easy ways to permute axes, so you can do basically the same thing. Things like Einstein notation, are built into the libraries, and then it's trivially easy to have them run on GPUs or TPUs or whatever. So it's for the last few years of my life, nearly all the code I write is array programming code, even though I'm not using a purely array language.
All right, so where do we start now with the questions? I'll let Bob and Adam go first if they want, and if they don't have okay, Bob, you go ahead.
I've got a quick question about neural networks and stuff, because when I was going to university all those years ago, people were talking about neural networks, and then they just sort of dropped off the face. And as you said, around 2010, suddenly they resurfaced again.
Yeah.
What do you think was the cause of that resurfacing? Was it hardware? Was it somebody discovered a new method, or what?
Yeah, mainly hardware. So what happened was people figured out how to do GPU, so general purpose GPU computing. So before that, I tried a few times to use GPUs for neural nets. I felt like that would be the thing. But GPUs were all about like creating shaders and whatever. And it was a whole jargon thing. I didn't even understand what was going on. So the key thing was NVIDIA coming up with this CUDA approach, which it's all loops, right? But it's much easier than the old way. Like the loops, you basically it's kind of loops. At least you basically say to CUDA, this is my kernel, which is the piece of code I want to basically run on each symmetric multiprocessing unit, and then you basically say launch a bunch of threads, and it's going to call your kernel. Basically incrementing the x and y coordinates and passing it to your kernel or making them available to your kernel. So it's not exactly a loop, but it's more like a map, I guess. And so when CUDA appeared, very quickly, neural network libraries appeared that would take advantage of it. And then suddenly, you get orders of magnitude more performance, and it's cheaper, and you get to buy an NVIDIA graphics card with a free copy of Batman, on the excuse that actually this is all for work. So it was mainly that. There's also this just like at the same time, the thing I'd been doing for 25 years suddenly got a name, data science. There's this very small industry of people like applying data-driven approaches to solving business problems. And we were always looking for a name. Not many people know this, but back in the very early days, there was an attempt at calling it industrial mathematics. Sometimes people would like shoehorn it into operations research or management science, but that was almost exclusively optimization people, and specifically people focused more on linear programming approaches. So yeah, once data science appeared, and also like, basically every company had finally built their data warehouse and the data was there. So yeah, it was like a more awareness of using data to solve business problems, and for the first time, availability of the hardware that we actually needed. And as I say, in 2012, it reached the point, like it'd been growing since the first neural network was built in, what was that, 1957, I guess, at this kind of gradual rate. But once it passed human performance on some tasks, it just kept going. And so now, in the last couple of months, it's now like getting decent marks on MIT math tests and stuff. It's on an amazing trajectory.
Yeah, it's kind of a critical mass kind of thing. You get a certain amount of information and it able to process that information. It, I guess, as you do with your hand, it's an exponential curve.
Yeah.
And humans and exponential curves, I think we're finding over and over again, we're not really great at understanding an exponential curve.
No, we're not. And that's like why I promised myself that as soon as I saw neural nets starting to look like they're doing interesting things, I would drop everything and jump on it, because I wanted to jump on that curve as early as possible. And we're now in this situation where people are just making huge amounts of money with neural nets, which they then reinvest back into making the neural nets better. And so we are also seeing this kind of bifurcation of capabilities where there's a small number of organizations who are extremely good at this stuff and have invested in it, and a lot of organizations that are, really struggling to figure it out.
And because of the exponential nature, when it happens very quickly. It feels like you didn't see it coming and suddenly it's there and then it was past you. And I think we're all experiencing that now.
Yeah, and it's happened in so many industries. Back in my medical startup, we were interviewing folks around medicines. We interviewed a guy finishing his PhD in histopathology, and I remember he came in to do an interview with us, and he basically gave us a presentation about his thesis on kind of graph cut segmentation approaches for pathology slides. And at the end, he was like, anyway, that was my PhD. And then yesterday, because I knew I was coming to see you guys and I heard you like neural nets, I just thought I'd check out neural nets. And about 4 hours later, I trained a neural net to do the same thing I did for my PhD. And it way outperformed my PhD thesis I'd spent the last 5 years on. And so that's where I'm at, and we hear this a lot.
Existential crisis in the middle of an interview.
Yes.
So I kind of have, I don't know, this is like a 1A, B, and C. And I'm not sure if I should ask them all at once. But so you said sort of at the tail end of the 90s is when your array language journey started. But it seems from the way you explained it that you had already at some point along the way heard about the array languages, APL and J, and have sort of alluded to, picking up some knowledge about the paradigm and the languages. So my first part of the question is sort of, at what point were you exposed to the paradigm in these languages? The second part is what's causing you in 2022 to, really dive into it? Because you said you feel like maybe a bit of an imposter or the least qualified guest, which probably is you just being very modest. I'm sure you know still quite a bit. And then the third part is, do you have thoughts about, and I've always sort of wondered, how the array language paradigm sort of missed out on, and Python ended up being the main data science language, while there's an article that's floating around online called Numpy, the Ghost of Iverson, which it's this sort of, you can see that in the names and the design of the library that there is a core of APL, and even the documentation acknowledges that it took inspiration greatly from J and APL, but that the array languages clearly missed what was a golden opportunity for their paradigm. And we ended up with libraries and other languages. So I just asked 3 questions at once, but yeah, feel free to tackle them in any order.
I have a pretty bad memory, so I think I've forgotten the second one already. So you can feel free to come back to any or all of them. So my journey, which is what you started with, was I always felt like we should do more stuff without using code. Because or at least kind of traditional, what I guess we'd call nowadays imperative code. Um, there was a couple of tools in my early days which I've got huge amounts of leverage from because nobody else in at least the consulting firms or generally in our clients knew about them. Now, that was SQL and pivot tables. And so pivot tables, if you haven't come across it, was basically one of the earliest approaches to OLAP, slicing and dicing. There was actually something slightly earlier called Lotus Improv, but that was actually a separate product. Excel was basically the first one to put OLAP in the spreadsheet. So no loops. You just drag and drop the things you want to group by, and you right-click to choose how to summarize. And same with SQL, you declaratively say what you want to do. You don't have to loop through things. SAS actually had something similar, with SAS, you could basically declare a prop that would run on your data. So yeah, I kind of felt like this was the way I would rather do stuff if I could. And I think that's what led me when we started doing the C++ implementation of the insurance pricing stuff, of being much more drawn to these metaprogramming approaches. I just didn't want to be writing loops in loops and dealing with all that stuff. I'm too lazy, to do that. I think I'm very driven by laziness, which, as Larry Wall said, is one of the 3 virtues of a great programmer. So I think as soon as I saw Numpy had reached a level of some, reasonable competence in Python, I was very drawn to that because it was what I've been looking for. And I think maybe that actually is going to bring us to answering the question of like what happened to array languages. Python has a lot of problems, but at its heart, it's a very well-designed language. It has a very small, flexible core. Personally, I don't like the way most people write it, but it's so flexible. I've been able to create almost my own version of Python, which is very functionally oriented. I basically have stolen the type dispatch ideas from Julia, created an implementation of that in Python. My Python code doesn't look like most Python code, but I can use all the stuff that's in Python. So there's this very nicely designed core of a language, which I then have almost this DSL on top of, and Numpy is able to create this kind of DSL, again, because it's working on such a flexible foundation. Ideally, so Python also has another DSL built into it, which is math. I can use the operators plus, times, minus. That's convenient. And in every array library, NumPy, PyTorch, TensorFlow, and Python, those operators work over arrays and do broadcasting over axes and so forth, and accelerate on an accelerator like a GPU or a TPU. That's all great. My ideal world would be that I wouldn't just get to use plus, times, and minus, but I'd get to use all the APL symbols. That would be amazing. But given a choice between a really beautiful language, at its core, like Python, in which I can then add a slightly cobbled together DSL like NumPy, I would much prefer that over a really beautiful notation like APL, but without the fantastic language underneath. Like I don't feel like there's nothing about APL or J or K's like programming language that attracts me. Do you know what I mean? I feel like in terms of like what I could do around whether it be type dispatch or how OO is designed, or how I package modules, or almost anything else, I would prefer the Python way. So I feel like that's basically what we've ended up with. You kind of either compromise between a good language with slightly substandard notation, or amazingly great notation with the substandard language, or not just language but ecosystem. Python has an amazing ecosystem. I think I hope one day we'll get the best of both, right? Like, here's my okay, here's my controversial take, and it may just represent my lack of knowledge. What I like about APL is its notation. I think it's a beautiful notation. I don't think it's a beautiful programming language. I think some things, possibly everything, but some things work very well as a notation. But to raise something to the point that it is a notation requires some years of study and development, and often some genius, like the genius of Feynman diagrams or the genius of juggling notation. Like there are people who find a way to turn a field into a notation, and suddenly they blow that field apart and make it better for everybody. For me, like, I don't want to think too hard all the time. Every time I come across something that really hasn't been turned into a notation yet, sometimes I just want to get it done, and so I would rather only use notation when I'm in these fields that either somebody else had figured out how to make that a notation, or I feel like it's really worth me investing to figure that out. Otherwise, there are, and the other thing I'd say is we already have notations for things that aren't APL that actually work really well, like regular expressions, for example. That's a fantastic notation, and I don't want to replace that with APL glyphs. I just want to use regular expressions. So yeah, my ideal world would be one where I can write PyTorch code, but maybe instead of like Einstein operations, Einstein notation, I could use APL notation. That I think that's where I would love to get to one day, and I would love that to totally transparently run on a GPU or TPU.
Wouldn't we all? Wouldn't we all?
As well, that would be my happy place.
Has no reason to do with the fact that I work at NVIDIA that I would love that, but interesting. I've never heard that before. The difference between basically appreciating or being in love with the notation, but not the language itself.
Mm-hmm. And it started out as a notation, right? Like Iverson talked, it was a notation they used for representing state machines or whatever on early IBM hardware. When he did his Turing Award essay, he chose to talk about his notation. And you see with people like Aaron with his co-defn stuff, that if you take a very smart person and give them a few years, they can use that notation to solve incredibly challenging problems like build a compiler, and do it better than you can without that notation. So I'm not saying APL can't be used for almost anything you want to use it for, but a lot of the time we don't have 5 years to study something very closely. We just want to, we've got to get something done by tomorrow.
Interesting.
We still didn't get a answer to.
Oh yeah, part 2.
When did you first meet APL, or how did you even find APL?
I first found Jay, I think, which obviously led me to APL, and I don't quite remember where I saw it. And actually, when I got to San Francisco, so that would be, I'm trying to remember, 2010 or something, I'm not sure. I actually reached out to Eric Iverson and I said, we're starting this machine learning company called Kaggle, and I kind of feel like, everybody does stuff in Python, and it's kind of in a lot of ways really disappointing. I wish we were doing stuff in J, but we really need everything to be running on the GPU, or at least everything to be automatically using SIMD and multiprocessor everywhere. He was kind enough to actually jump on a Skype call with me. Not just jump on a Skype call, but it's like, how do you want to chat? And it's like, how about Skype? And he created a Skype account and chatted. And like, oh, yeah, we chatted for quite a while. We talked about, these kinds of hopes, and Yeah, but I just, never really, because neither J or APL is in that space yet. There was just never a reason for me to do anything other than like, I kind of felt like each time I'd have a bit of a break for a couple of months, I'd always spend a couple of weeks fiddling around with J just for fun. But that's as far as I got, really.
Yeah, I think the first time I'd heard of you was in an interview that Leo Laporte did with you on triangulation, and you were talking about kaggle. That was a specific thing. But I think I was riding my bike along some logging road or something, and suddenly he said, "Oh yeah, but a lot of people use J. I like J." It's the first time I'd ever heard anybody on a podcast say anything about J. It was just like, wow, that's amazing. I didn't know what, like, and the whole interview about kaggle, there was so much of it about the importance of data processing, not just having a lot of data, but knowing how to filter it down, not over filtering, all those tricks. I'm thinking, wow, these guys are really doing some deep stuff with this stuff, and this guy is using J. I was actually very surprised at that point that somebody, I guess not that somebody who was working so much with data would know about J, but just that it would be, I guess, just suddenly popped onto my headsets, and I'm just, wow, that's so neat.
Yeah. And I will say, like, in the array programming community, I find there seems to be a common misconception that like the reason people aren't using array programming languages is because they don't know about them or don't understand them, which there's a kernel of truth of that. But the truth is, like, nowadays there's huge, massively funded research labs at places like Google Brain and, Facebook AI Research and OpenAI and so forth, where large teams of people are literally writing new programming languages because they've tried everything else and what's out there is not sufficient. I find there's, in the array programming world, there's often a huge kind of underappreciation of what Python can do nowadays. For example, like I as recently as last week, I heard it described in a chat room as like, people obviously don't care about performance because they're using Python. And it's like, well, a large amount of the world's highest performance computing now is done with Python. Like it's not because Python's fast, it's because but if you want to use Rapids, for example, which literally holds records for the highest performance, recommendation systems and tabular analysis, you write it in Python. That's, so this idea of having a fast kernel that's not written in the language and then something else talking to it in a very flexible way, I think is great. And as I say, at the moment, we are very hamstrung in a lot of ways that we, or at least until recently, we very heavily relied on BLAS, which is totally the wrong thing for that kind of flexible high performance computing, because it's this, bunch of somewhat arbitrary kind of selection of linear algebra algorithms, which, things like the C# work I did, they were just wrappers on top of BLAS. And what we really want is a way to write really expressive kernels that can do anything over any axes. So then there are other newer approaches like Julia, for example, which is kind of like got some Lispy elements to it and this type dispatch system. But because it's, in the end, it's on top of LLVM, what you write in Julia, it does end up getting optimized very well, and you can write pretty much arbitrary kernels in Julia and often get best-in-class performance. And then there's other approaches like JAX, and JAX sits on top of something totally different, which is it sits on top of XLA. And XLA is a compiler which is mainly designed to compile things to run fast on Google's TPUs, but it's also does an okay job of compiling things to run on GPUs. And then really excitingly, I think, for me is the MLIR project, and particularly the affine dialect. So that was created by my friend Chris Latner, who you probably know from creating Clang and LLVM and Swift. So he joined Google for a couple of years, and we worked really closely together on trying to think about the vision of really powerful programming on accelerators that's really developer friendly. Unfortunately, didn't work out. Google was a bit too tied to TensorFlow. But one of the big ideas that did come out of that was MLIR, and that's still going strong. And I do think there's, if something like APL, could to target MLIR and then become a DSL inside Python, it may yet win.
I've heard you in the past say that on different podcasts and talks that you don't think that Python, like even in light of just saying people don't realize how much you can get done with Python, that you don't think that the future of data science and AI and neural networks and that type of computation is going to live in the Python ecosystem. And I've heard on some podcasts you've said that Swift has a shot based on sort of the way that they've designed that language, and you just mentioned a plethora of different sort of, I wouldn't say initiatives, but JAX, XLA, Julia, et cetera. Do you have a sense of where you think the future of not necessarily sort of array language computation, but this kind of computation is going with all the different avenues?
Yeah, I do. I think we're certainly seeing the limitations of Python and the limitations of the PyTorch, lazy evaluation model, which is the way most things are done in Python at the moment for kind of array programming is you have an expression which is working on arrays, possibly of different ranks with implicit looping, and that's one line of Python code, and generally that then gets on your computer that'll get turned into a request to run some particular optimized pre-written operation on the GPU or TPU. It then gets sent off to the GPU or TPU where your data has already been moved there. It runs, and then it tells the CPU when it's finished. And there's a lot of latency in this, right? So if you want to create your own kernel, like your own way of doing, your own operation effectively, good luck with that. That's not going to happen in Python. And I hate this. I hate it as a teacher because, I can't show my students what's going on, right? It kind of goes off into, kind of CUDA land and then comes back later. I hate it as a hacker because I can't go in and hack at that. I can't trace it. I can't debug it. I can't easily profile it. I hate it as a researcher because very often I'm like, I know we need to change this thing in this way, but I'm damned if I'm going to go and write my own CUDA code, let alone deploy it. So JAX is, I think, a path to this. It's where you say, okay, let's not target pre-written CUDA things. Let's instead target a compiler. And working with Chris Lattner, I'd say he didn't have too many nice things to say about XLA as a compiler. It was not written by compiler writers. It was written by machine learning people, really. But it does the job, and it's certainly better than having no compiler. And so JAX is something which, instead of turning our line of Python code into a call to some pre-written operation, it instead is turning it into something that's going to be read by a compiler. And so the compiler can then, optimize that as compilers do. So yeah, I would guess that JAX probably has a part to play here, particularly because you get to benefit from the whole Python ecosystem, package management, libraries, visualization tools, etc. But longer term, it's a mess. It's a mess using a language like Python, which wasn't designed for this. It wasn't really even designed as something that you can chuck different compilers onto. So people put horrible hacks. So for example, PyTorch, they have something called TorchScript, which is a bit similar. It takes Python and kind of compiles it, but they literally wrote their own parser using a bunch of regular expressions, and it's not very good at what it does. It even misreads comments and stuff. So I do think there's definitely room for a language, of which Julia would certainly be the leading contender at the moment, to come in and do it properly. And Julia is written on a scheme basis. So there's this little scheme kernel that does the parsing and whatnot, and then pretty much everything else after that is written in Julia. And of course, leveraging LLVM very heavily. But I think that's what we want, right? Is that something which, I guess something also I didn't love about Swift, when the team at Google wanted to add differentiation support into Swift, they wrote it in C++. And I was just like, that's not a good sign. Apart from anything else, you end up with a group of developers who are, in theory, Swift experts, but they actually write everything in C++. And so they actually don't have much feel for what it's like to write stuff in Swift. They're writing stuff for Swift. In Julia, pretty much everybody who's writing stuff for Julia is writing stuff in Julia. And I think that's something you guys have talked about around APL and J as well, is that there's the idea of writing J things in J and APL things in APL is a very powerful idea.
Yeah, I always wonder about...
Oh, yeah, sorry, go on. I just remembered your third question. I'll come back to it.
No, you go ahead.
You asked me why now am I coming back to APL and J, which is totally orthogonal to everything else we've talked about, which is I had a daughter. She got old enough to actually start learning math, so she's 6. Oh my God, there's so many great educational apps nowadays. There's one called Dragonbox Algebra. It's so much fun. Dragonbox Algebra 5 Plus. And I was like, 5 Plus Algebra? Like, what the hell? So when she was, I think actually she was still 4, I let her play with Dragonbox Algebra 5 Plus. And she learned algebra, by helping dragon eggs hatch. And she liked it so much, I let her try doing Dragonbox Algebra 12 Plus. And she loved that as well and finished it. And so suddenly I had a 5-year-old kid that liked algebra. Much to my surprise. Kids really can surprise you. And so, yeah, she struggled with a lot of the math that they were meant to be doing at primary school, like division and multiplication, but she liked algebra. And we ended up homeschooling her. And then one of her best friend is also homeschooled. So this year I decided I'd try tutoring them in math together. And so my daughter's name's Claire. So her friend Gabe. Discovered on his Mac the world of alternative keyboards. So he would start typing in the chat in, Greek characters or Russian characters. And one day I was like, okay, check this out. So I typed in some APL characters, and they were just like, wow, what's that? We need that. So initially we installed Dyalog APL so that they could type APL characters in the chat. And so I explained to them that this is actually this super fancy math that you're typing in. And they really wanted to try it. So, and that was at the time I was trying to teach them sequences and series, and they were not getting it at all. It was my first total failure time as a math tutor with them. They'd been zipping along, fractions, greatest common denominator, factor trees. Okay, everything's fine. It makes sense. And then we hit sequences and series, and it's just like they had no idea what I was talking about. So we put that aside. Then we spent 3 one-hour lessons doing the basics of APL, the basic operations and doing stuff with lists and dyadic versus monadic, but still, just primary school level math. And we also did the same thing in Numpy using Jupyter. And they really enjoyed all that. They were more engaged than our normal lessons. And so then we came back to sigma I equals 1 to 5 of I squared, whatever. And I was like, okay, that means this, in APL and this in NumPy. And they're like, oh, is that all? Fine. That's like, yeah, so that was the problem. This idea of like Tn equals Tn minus 1 plus blah, blah. It's like, what is this stuff? But when you're actually indexing real things and can print out the intermediate values and all that, and you've got iota or a range, they were just like, oh, okay. I don't know why you explained it this dumb way before. And I will say, given a choice between doing something on a whiteboard or doing something in Numpy or doing something in APL, now they'll always pick APL because the APL version is just so much easier. There's less to type, there's less to think about, there's less boilerplate. And so it's only been a few weeks, but like yesterday, we did the power operator, and so we literally started doing the foundations of mathematics. So it's like, okay, let's create a function called capital S arrow, plus jot 1, right? So for those Python people listening, jot is if you give it an array or a scalar, it's the same as partial in Python, or bind in C++. So, okay, we've now got something that adds 1 to things. Okay, I said, okay, this is called the successor function. And so I said to them, okay, what would happen if we go SSS0? And they're like, oh, that would be 3. And so I said, okay, well, what's addition? And then one of them's like, oh, it's repeated S. I'm like, yeah, it's repeated S. So how do we say repeated? So in APL, we say repeated by using this star diaresis. It's called power. Okay, so now we've done that. What is multiplication? And then one of them goes, after a while, oh, it's repeated addition. So we define addition, and then we define multiplication. And then I'm like, okay, well, what about, exponent? Oh, that's just, now this one they've heard 1,000 times. They're both immediately like, oh, that's repeated multiplication. So like, okay, we've now defined that. And then, okay, well, subtraction, that's a bit tricky. Well, it turns out that subtraction is just, is the opposite of something. What's it the opposite of? They both know. Like, oh, that's the opposite of addition. Okay, well, opposite of, which in math we call inverse, is just a negative power. So now we define subtraction. So how would you define division? Oh, okay. How would you define roots? Oh, okay. So we kind of like, designing the foundations of mathematics here at APL, with a 6-year-old and an 8-year-old. And during this whole thing, at one point, we're like, okay, well, now I can't remember why, but we're like, okay, now we've got to do 1 divided by a half. And they're both like, we don't know how to do that. So, with APL, this stuff that's considered like college level math suddenly becomes easy. And, at a point when still primary school level math, like 1 divided by a half, is still considered hard. So it's definitely made me rethink, what is easy and what is hard and how to teach this math stuff. And so I've been doing a lot of teaching of math with APL, and the kids are loving it and I'm loving it. And that's actually why I started this study group, which will be on today. Today, as we record this, a few days ago, as you put it out there, is I kind of started saying on Twitter to people like, oh, it's really been fun teaching my kids, my kid and her friend math using APL. And a lot of adults were like, can we learn math using APL as well? So that's what we're going to do.
Well, and that's the whole notation thing, isn't it?
Uh-huh.
It's the notation. You get away from the sigmas and the pies and all that, subscripts.
I know, right?
This is exactly what Iverson wanted.
Exactly. I mean, who wants this, why should capital pi be product and capital sigma be sum? It's like, we did plus slash, and then it's like, okay, how do we do product? And they're like, oh, it's obviously times slash. And I show them backslash. It's like, how do we do a cumulative product? And so, oh, it's obviously times backslash. Yeah, this stuff. But a large group of adults can't handle this, because I'll put stuff on Twitter. I'll be like, here's a cool thing in APL. And like half the replies will be like, well, that's line noise. That's not intuitive.
How do you type that?
It's this classic thing that Iverson always said. It's like the difference between is it that you don't understand it, or is it that it's hard? And, kids don't know, for kids, everything's new. So that, if they see something they've never seen before, they're just like, teach me that. Whereas adults, or at least a good chunk of adults, are just like, I don't immediately understand that, therefore it's too hard for me, therefore I'm going to belittle the very idea of the thing.
I did a tacit program on one-liner on APL Farm the other day, and somebody said, that looks like Greek to me. I said, well, Greek looks like Greek to me because I don't know Greek.
Right.
I mean, sure, if you don't know it, absolutely it looks silly. But if you know it, then it's not that hard.
Yeah, I will say, like, you know, a lot of people have put a lot of hard work into resources for APL and J teaching, but I think there's still a long way to go. And one of the challenges is, it's like when I was learning Chinese, I really wanted to, I liked the idea of learning Chinese new words by looking them up in a Chinese dictionary. But of course, I didn't know what the characters in the dictionary meant, so I couldn't look them up. So when I learned Chinese, I really spent the first 18 months just focused on learning characters. So I got through 6,000 characters in 18 months of very hard work. And then I could start looking things up in dictionary. My hope is to do a similar thing for APL, like for these study groups. I want to try to find a way to introduce every glyph in an order that never refers to glyphs you haven't learnt yet. Like that's something I don't feel like we really have. And so that then you can look up stuff in the Dyalog documentation, because now still I don't know that many glyphs. So like most of the stuff in the documentation I don't understand because it explains glyphs using glyphs I don't yet know, and then I look those up and those are used explain things with glyphs I don't yet know. So, you know, step one for me is I think we're just going to go through and try to teach what every glyph is. And then I feel like we should be able to study this better together, because then we can actually read the documentation, you know.
Are you going to publish these sessions online?
Yeah, so the study group will be recorded as videos, but I also then want to actually create, you know, written materials using Jupyter, which I will then publish. That's my goal.
So what you said very much resonates with me, that I often find myself in when teaching people this bind that to explain everything I need to already have everything explained. And I think so, and especially it comes down to, in order to explain what many of these glyphs are doing, I need some fancy arrays. If I restrict myself to simple vectors and scalars, then I can't really show their power. And I cannot create these higher rank arrays without already using those glyphs.
Right.
And so hopefully, it was this long running project since like 2015, I think it is to add a literal array notation to APL.
Right.
And then there is a way in. Then you can start by looking at what is an array, and then you can start manipulating and see the effects of the glyphs and intuit from there what they do.
Yeah, no, I think that'll be very, very helpful. And in the meantime, you know, my approach with the kids has just been to teach row quite early on.
Right.
So row is the equivalent of reshape in Python, most Python libraries. And yeah, so once you know how to reshape, you can start with a vector and shape it to anything you like. And it's, you know, it's not a difficult concept to understand. So I think that, yeah, basically the trick at the moment is just to say, okay, in our learning of the dictionary of APL, one of the first things we will learn is row. And then it was really fun with the kids doing monadic row, you know, to be like, okay, well, what's row of this? And what's row of that? And okay, what's row of this? And then what's row of row of row? Which then led me to the Storman poem about what is it? Row is one, et cetera, which they loved as well.
Yeah, we'll link that in the show notes. Also, too, while you were saying all that, that really resonated with me when I first started learning APL is like one of the first things that happened when I was like, oh, okay, you can fold, you can map. So like, how do you filter? You know, what are the classic, you know, 3 functional things? And the problem with APL and array languages is they don't have an equivalent filter that takes a predicate function. They have a filter that is called compress that takes a mask that, you know, drops anything that corresponds to a 0. And it wasn't until a few months later that I ended up discovering it. But for both APL and the newer APL BQN, there's these 2 sites. Adam was the one that wrote the APL one, applecart.info and baconcrate.info, I also think. And so you can basically semantically search for what you're trying to do. and it'll give you small expressions that do that. So if you type in the word filter, which is what you would call it coming from, a functional language, or even I think Python calls it filter, you can get a list of small expressions, and really, really often, sometimes you need to know the exact thing that it's called. Like one time I was searching for, all the combinations or permutations, and really what I was looking for was power set. And so until you have that, the word power set, it's a fuzzy search, right? So, but it's still a very, very useful tool when it's like you said, you're trying to learn something like Chinese, and it's like, well, where do I even start? I don't know the language to search, the words to search for. But yeah, it is. I agree that there's a large room for improvement in how to onboard people without them immediately going, like you said, this looks like hieroglyphics, which I think Iverson considered a compliment. Like there's some anecdote I've heard where someone was like, this is hieroglyphics. And he says, yes, exactly. And then they both just.
I think the other thing that I want to do is help, in particular, Python programmers, and maybe also do something for JavaScript programmers, which are the two most popular languages. Like at the moment, like a lot of the tutorials for stuff like J or whatever, like J for C programmers, great book, but most people aren't C programmers. And also a lot of the stuff it'd be so much easier if somebody just said to me early on, oh, jot's just the same as partial in Python, or it's like, putting things in a box. What the hell's a box? If somebody basically said, oh, it's basically the same as a reference. And it's like, oh, okay. I think in one of your podcasts, somebody said, oh, it's like void star. It's like, oh, yeah, okay. There's this kind of lack of just saying this is actually the same thing as blah in Python and JavaScript. So I do want to do some kind of, mapping like that, particularly for kind of NumPy programmers and stuff, because a lot of it's so extremely similar. Be nice to kind of say okay, well, this is, J maps things over leading axes, which is exactly the same as NumPy, except it does it over trailing axes. So if you know the NumPy rules, you basically know the J rules.
Yeah, I think at the basic level, you're absolutely right, and that would certainly be really useful. When we've talked this over before, some of the challenges are in the flavors and the details. If you send somebody down the wrong road with a metaphor that almost works in some of these areas, it can really be challenging for them, because they see it through their lens of their experience, but that would say in this area it would work differently than it actually does. So there is a challenge in that, and we find it even between APL, BQN, and J. I'm trying to think of what we were talking about recently. Oh, it was transpose.
Dyadic transpose. Yeah.
The languages, dyadic transposes, they handle them differently. They're functionally, you can do the same things, but you have to be aware that they are going to do it differently according to the language.
Absolutely. But that's not a reason to throw out the analogy, right?
No.
I think everybody agrees that it's easier for an APL programmer to learn J than for a C or JavaScript programmer to learn J. Because there are some ideas you understand, and you can actually say to people okay, well, this is the rank conjunction in J, and you may recognize this as being like the rank, operator in APL. So if we can do something like that and say oh, well, okay, this is, this would do the same thing as, dot permute, dot blah in PyTorch. It's okay, I see it.
Well, as the maintainer of Apple Cart, I'd like to throw in a little call to the listeners, like what Connor mentioned. I do fairly often get people saying, well, I couldn't find this and this, and I ask them, what did you search for? So do let me know, contact me by whatever means. Say if you couldn't find something, either because it's altogether missing and I might be able to edit, or tell me what you searched for and couldn't find, or maybe you found it later by searching for something else, and I'll add those keywords for future users. And I have put in a lot of function names from other programming languages so that you can search for those and find the APL equivalent.
I will say I feel like either I'm not smart enough to use applecart.info, or I haven't got the right tutorial yet, because I went there. I've been there a few times, and there's this whole lot of impressive looking stuff, and I don't want to know what to do with it. And then I sometimes click things and it sends me over to this tio.run that tells me real time 0.02 seconds code. I find it, a little, not a little. I have not yet. I don't yet know how to use it, and so but I guess hearing you guys say this is a really useful tool that a lot of people put a lot of time into, I should obviously invest time learning how to use it, and maybe after doing that, I should explain to people how to use it.
I do have a video on it, and there's also a little question mark icon one can click on and get to the instructions.
I have tried the question mark icon as well. As I say, it might just, I think this often happens with APL stuff. I often hit things and I feel like maybe I'm not smart enough to understand this.
Clearly don't think that's if you're hitting a wall.
I don't think that's the problem.
We humbly disagree. But,
I do recall you saying a few minutes ago that you managed to teach your 4-year-old daughter like 12 grade or age 12 algebra.
No, I didn't. I just gave her the app. Right? It's like I've heard other parents are giving it to their kids. They all seem to handle it. It's just this fun game where you hatch dragon eggs by like dragging things around on the iPad screen, and it so happens that the things you're doing with dragon's eggs are the rules of algebra. And after a while, it starts to switch out some of the like monsters with symbols like X and Y, and it does it gradually. And at the end, it's like, oh, now you're doing algebra. So I can't get any credit for that. That's some very, very clever people wrote the very cool things.
It really is an amazing program. I homeschooled my son as well, and we used that for algebra.
Yeah.
And he was a bit more age appropriate, but I looked at that and said that really is well put together.
Yeah.
It's an amazing program. Yeah.
Maybe there'll be a Dragon Box APO one day.
Hey, that's not a bad idea.
Yeah.
Not a bad idea at all. I was going to say, when you're teaching somebody, one of the big challenges when you're sort of trying to get a language across to a general audience is who is the audience. Because, as you say, if you're dealing with kids or people who haven't been exposed to programming before, that's a very different audience than somebody might have been exposed to some other type of programming. Functional programming is a bit closer, but if you're procedural programmer, imperative programmer, it's going to be a stretch to try and bend your mind in the different ways that, APL or J or BQN expect you to think about things.
Yeah, I think the huge rise of functional programming is very helpful for coming to array programming, both in JavaScript and in Python. It's, I think most people are doing stuff, particularly in the machine learning and deep learning world, are doing a lot of functional stuff. Often that's the only way you can do things, particularly in deep learning. So I think that does help a lot. Like Connor said, like you've probably come across, map and reduce and filter, and certainly in Python you'll have done list comprehensions and dictionary comprehensions, and a lot of people have done SQL. So I think a lot of people come into it with some relevant analogies if we can help connect it for them.
Yeah, one of the things that is really it's reinforcing my idea that, or it's not my idea. I think it's just an idea that multiple people have had, but the tool doesn't exist yet. Because we'll link to some documentation that I use frequently when I'm going sometimes between APL and J on the BQN website. They have BQN to Dyalog APL dictionaries and BQN to J dictionary. So sometimes I'll if I'm trying to convert between the two, the BQN docs are so good, I'll just use BQN as like an IR to go back and forth. But I've mentioned on previous podcasts that really what would be amazing, and it would only work to a certain extent, is something like a multi-directional array language transpiler. And adding NumPy to that list would probably be, a huge, I don't know what the word for it is, but beneficial for the array community if you can type in some NumPy expression. Like I said, it's only going to work to an extent, but for simple, rank 1 vectors or arrays that you're just reversing and summing and doing simple, reduction and scan operations, you could translate that pretty easily into APLJ and BQN. And I think that would make it so much easier for people to understand, aka the hieroglyphics or the Greek or the Chinese or whatever metaphor you want to use. Because it is definitely challenging at times to get to a certain point where you have enough info to keep the snowball rolling, if you will. and it's very easy to hit a wall early on. And
So that's a project I've been thinking about. Is basically rewrite NumPy in APL. It doesn't seem like a whole lot of work. Where just take all those names that are available in NumPy and just define them as APL functions, and people can explore that by opening them up and seeing how they're defined.
Oh, so not actually you're saying like it wouldn't be a new thing. You're just saying like rename the symbols what they're known as in NumPy so that you'd still be in like an APL.
Yeah, I mean, you could use it as a library, but I was thinking of it more as an interactive exploring type thing, where you open up this library and then you write the name of some NumPy thing functionality and open it up in the editor and see, well, how is this defined in APL? And then you could use it, obviously, since it's defined. Then you could use these library functions, and then as you get better at APL, you can start actually writing out the raw APL instead of using these covers for it.
Well, I guess, Jeremy, that's an interesting. Do you think that, because you've mentioned about sort of the notation versus the programming language, and where do you think in your dream scenario, are you actually coding in sort of an Iversonian-like notation, or
No.
is it at the end of the day, does it still look like NumPy, but it's just all of the expressivity and power that you have in the language like APL is brought to and combined with what NumPy sort of currently looks like?
I mean, well, it would be a bit of a combination, Connor, in that, like, my classes and my type dispatch and my packaging and, all the, my function definitions and whatever, that's Python. But, everywhere I can use plus and times and divide and whatever, I could also use any APL glyph. And so it'd be, basically an embedded DSL for kind of high dimensional notation. It would work automatically on NumPy arrays and TensorFlow tensors and PyTorch tensors. I mean, one thing that's interesting is, to a large degree, APL and PyTorch and friends have actually arrived at a similar place with the same, grandparents, which is, Iverson actually said his inspiration for some of the APL ideas was tensor analysis. And a lot of the folks, as you can gather from the fact that in PyTorch we don't call them arrays, we call them tensors, a lot of the folks working on deep learning, their inspiration was also from tensor analysis. So it comes from physics, right? And so I would say, a lot more folks that worked on PyTorch were familiar with tensor analysis and physics than were familiar with APL. And then of course there's been other notations, like explicitly based on Einstein notation. There's a thing called INOPS, which it's a very interesting kind of approach of taking Einstein notation much further. And like Einstein notation, if you think about it, is the kind of the loop-free programming of math, right? The equivalent of loops in math is indices. And Einstein notation does away with indices. And so that's why stuff like INOPS is incredibly powerful, because you can write, an expression in INOPS with no indices and no loops, and it's all implicit reductions and implicit loops. I guess, my ideal thing would be, we wouldn't have to use INOPS. We can use APL, and it wouldn't be embedded in a string. They would actually be operators. Yeah, that's what it is. There'd be operators in the language. That Python operators would not just be plus, times, minus, slash, but would be all the APL glyphs would be Python operators, and they would work on all Python data types, including all the different tensor and array data types.
Interesting. Yeah. So it sounds like you're describing a kind of hybrid language that.
Yeah, JavaScript too. I would love the whole DSL to be in JavaScript as well. That'd be great. And I feel like I saw that somewhere. I feel like I saw somebody actually do an ECMA script, RFC with an implementation of APL.
It was an April's Fool's joke.
Yeah, but it actually worked, didn't it? Like there was actually an implementation that.
I don't think they had the implementation. It was just very, very well spec'd. It could actually work, kind of thing.
No, I read the code. I don't know how complete it was, but there was definitely some code there. I can't find it again. If you know where it is.
There's a JavaScript implementation of APL by Nick Nikolov. But my problem with it, it's not tightly enough connected with the underlying JavaScript. It just allows you to.
But it shouldn't be an April Fool's joke, should it?
No, it shouldn't.
It's like Gmail was an April Fool's joke, right? Gmail came out on April the 1st and totally destroyed my plans for Fastmail because it was an April Fool's joke that was real. And Flask, the Flask library, I think, was originally an April Fool's joke of like, we basically saying we shouldn't be using frameworks because I've created a framework that's so stupidly small that it shouldn't be a framework. And now that's the most popular web framework in Python. So yeah, maybe this should be an April Fool's joke that becomes real.
How close? This is maybe an odd question, but because from what I know about Julia, you can define your own Unicode operators, and I did try at one point to create a small composition of two different symbols, square root and reverse or something, and it ended up not working and asking me for parentheses. But do you think Julia could evolve to be that kind of hybrid language that?
Yeah, maybe. Maybe. I'm actually doing a keynote at JuliaCon in a couple of weeks, so maybe I should raise that.
Just at the Q&A section, say any questions. But first, I've got one for the community at large. Here's what I'd like.
I think my whole talk's going to be kind of like what Julia needs to be, to move to the next level. Which I'm not sure I can demand that a complete APL implementation is that thing, but I could certainly put it out there as something to consider.
Well, it always bothers me though that if you try to extend those languages like this, or you could use some kind of pre-compiler for it, then their order of execution ends up messing up APL. I think APL very much depends on having a strict one-directional order of functions. Otherwise, it's hopeless to keep track of precedence.
Yeah, I mean, you'd have to that is a big challenge because currently the DSL inside Python, which is the basic mathematical operations, do have the BODMAS or PEMDAS order operations. So there would need to be some way. So in Python, that wouldn't be too hard actually, because in Python, you can opt into different kind of parsing things by adding a from dunder futures import BLAS. So you could have a from dunder futures import APL precedence. And then from then on, everything in your file is going to use right to left precedence.
That's really interesting and cool. I didn't know that.
I've been spending a lot of time thinking about function precedence and just the differences in different languages. And I'm not sure if any other languages have this, but it's something that I find very curious about BQN and APL is that they have functions basically that have higher precedence than other functions. So operators in APL and conjunctions and adverbs, they have higher precedence than your regular functions that apply to arrays. I'm simplifying a tiny bit, but this idea that like in Haskell, function application always has the highest precedence. You can never get anything that has a higher function precedence than that. And it always, having stumbled into the array world now, it seems like a very powerful thing that these combinator-like functions don't have just by default the higher precedence. Because if you have a fold or a scan or a map, you're always combining that with some kind of binary operation or unary operation to create another function that you're then going to eventually apply to something.
But the basic like right to left, putting aside the the higher order functions or operators as they're known in APL, the basic right to left path. I mean, again, for teaching and for my own brain, gosh, that's so much nicer than like in C++. Oh my God, the amount of operator precedence, there's no way I can ever remember that. And there's a good chance when I'm reading somebody else's code that, they haven't used parentheses because they didn't really need them and that I have no idea where they have to go. And then I have to go and look it up. And, it's another of these things that with the kids, I'm like, okay, you remember that stuff we spent ages on about like first you do exponents and then you do times. And it's like, okay, you don't have to do any of that in APL. You just go right to left. And they're just like, oh, that's so much better.
What is this literally came up at work like a month ago where I was giving this mini APL, like we had 10 minutes at the end of a meeting. And then I just made this offhand remark that, of course, like the evaluation order in APL is a much simpler model than what we learned in school. And like I upset, like there was, I don't know, 20 people in the meeting. And it was the most controversial thing I had said. and I almost had like an out of body experience because I thought I was saying something that was like objectively just true.
Yeah, well, you were.
And then I was like, wait a second, what? I'm clearly missed. Like, is there?
No, I mean,
am I doing something wrong? Like, how do you communicate?
Most adults are incapable of like new ideas. It's just.
That's what I should have said in the meeting.
This is another reason I like doing things like APL study groups, because it's a way of like self-selecting that small group of humanity who's actually interested in trying new things, despite the fact that they're grown-ups, and then try to surround myself with those people in my life.
But isn't it sad then? I mean, what has happened to those grown-ups? Like when you mentioned teaching these people and trying to like map their existing knowledge onto APL things, what does it mean to box and so on? I find that to children and non-programmers, explaining the array model and how the functions are applied and so on is almost trivial, meets no resistance at all. And it's all those adults that have either learned their PEMDAS or BODMAS or whatever the rules are, and all the computer science people that know their precedence tables and their lists of lists and so on. Those are the ones that are really, really struggling. It's not just resisting. They're clearly struggling. They're really trying, and it's a lot of effort.
Well, there is actually, that is a known thing in educational research. So I spent months earlier this year and late last year reading every paper I could about, education, because I thought if I'm going to be homeschooling, then I should try to know what I'm doing. And yeah, what you describe, Adam, is absolutely a thing, which is that the research shows that when you've got an existing idea, which is an incorrect understanding of something, and you're trying to replace it with a correct understanding, that is much harder than learning the correct version directly. So, which is obviously a challenge when you think about analogies. An analogy has to be good enough to lead directly to the correct version. But I think the important thing is to find the people who have the curiosity and tenacity to be prepared to go over that hurdle, even though it's difficult, because it is like that's just how human brains are. So be it,
Yeah, unlearning is really hard work, actually. And if you think about it, it probably should be, because you spend a lot of time and energy to put some kind of a pattern into your brain. You don't want to have that evaporate very quickly.
Right. And our, myelination occurs around like ages 8 to 12 or something. So like our brains are literally trying to stop us from having to learn new things, because our brains think that they've got stuff sorted out at that point, and so they should focus on keeping long-term memories around. So yeah, it does become harder, but a little bit. It's still totally doable.
The solution's obvious. Teach APL in primary school.
That's what I'm doing. Kind of.
What was the word you mentioned? Myelination?
Myelination, MEYLINATION.
Interesting. I had not heard that word before.
So it's a physical coating that I can't remember, goes on the dendrites or something.
I think it's on the axons, isn't it?
Axons. That sounds right.
Yeah, the transmission wire. Yeah.
You get these fat layers or cholesterol layers. Yeah.
I never took any biology courses in my education, so clearly I've missed out on that aspect.
You myelinated anyway.
Isn't that an APL function? Myelinate? I don't think so.
You also mentioned the word tenacity, Jeremy.
Yeah.
And I was watching an interview you did with Samyan Bhatani. And you were talking about, because it sounds like he was, you spotted at an early point in his working with Kaggle that he was something probably different. And the thing you said was the tenacity to keep working at something.
Yeah.
I think that's a really important part about educating people.
Oh, yeah.
That they shouldn't necessarily expect learning something new to be easy.
Yeah.
But you can do it.
Oh, yeah. I mean, I really noticed that when I started learning Chinese. Like I went to just some local class in Melbourne, and everybody was very, very enthusiastic, and everybody was going to learn Chinese. And we all talked about the things we were going to do. And yeah, each week there'd be fewer and fewer people there. And, I kind of tried to keep in touch with them. But after a year, every single other person had given up, and I was the only one still doing it. And, so then after a couple of years, people would be like, wow, you're so smart. You learn Chinese. And it's just like, no, man, like during those first few weeks, I was pretty sure I was learning more slowly than the other students. But everybody else stopped doing it. So, of course, they didn't learn Chinese. And I don't know what the trick is because, yeah, it's the same thing with, like at Fast.ai courses, they're really designed to keep people interested and get people doing fun stuff from day one. But, still, I'd say most people drop out. And the ones that don't, I would say most of them end up becoming like actual world-class practitioners, and they, build new products and startups and whatever else. And people will be like, oh, I wish I knew neural nets and deep learning. It's just like, okay, here's the course. Just do it and don't give up. But yeah, I don't know. Tenacity, it's not a very common virtue, I think, for some reason.
It's something I've heard, I think it's Joe Bowler at Stanford talk about the growth mindset. And I think that is something that, for whatever reason, some people tend to, and maybe it's myelination, at those ages, you start to get that mindset where you're not so concerned about having something happen that's easy to do well, but just the fact that if you keep working at it, you will get it. And not everybody, I guess, is maybe put in the situations that they get that feedback that tells you, if I keep trying this, I'll get it.
Yeah.
If it's not easy, they stop.
Yeah, I mean, that area of growth mindset's a very controversial idea in education. Specifically, the question of can you modify it? And I think it's certainly pretty well established at this point that the kind of stuff that schools have tended to do, which is put posters up around the place saying like, make things a learning opportunity or don't give up, like they do nothing at all. With my daughter, we do all kinds of stuff around this. So we've actually invented a whole family of clams. And as you can imagine, clams don't have a growth mindset. They tend to sit on the bottom of the ocean, not moving. And so the family of clams that we invented that we live with, always at every point that we're going to have to like learn something new or try something new, always start screaming and don't want to have anything to do with it. And, so we actually have Claire telling the clams how it's going to be okay. And, it's actually a good thing to learn new things. And so we're trying stuff like that to try to like have imaginary creatures that don't have a growth mindset, and for her to realize how silly that is, which is fun.
But even in the things that you were talking about in terms of the mathematics, you didn't say, "Oh, the successor. This is what plus is." You said,
"Yeah, for sure."
How would you use this? How would you? They start to have to put it together themselves, which to me that's the growth mindset.
Yeah.
That if you're creating
but
that.
Then like gosh, you're getting to all the most controversial things in education here, Bob, because that's the other big one is discovery learning. So this idea of having kids explore and find. It's also controversial because it turns out that actually the best way to have people understand something is to give them a good explanation. So it is important like that you combine this like, okay, how would you do this with then like, okay, let me just tell you what, why this is. It's easier for homeschooling with 2 kids because I can make sure their exploration is short and correct. If you spend a whole class, 50 minutes doing totally the wrong thing, then you end up with these really incorrect understandings, which you then have to kind of deprogram. So Yeah, education's hard, and I think a lot of people look for these simple shortcuts, and they don't really exist. So you actually have to, have good explanations and good problem-solving methods, and all this stuff. It's a really interesting area, though, and the tools.
And the tools and the notations become part of that.
Yeah, and notation. I mean, yeah. So I do a live coding, video thing every day with a bunch of folks, and in the most recent one, we started talking about APL, why we're going to be doing APL this week instead. And I gave, somebody actually said like, oh my God, is it going to be like regexes? And, I kind of said like, okay, so regexes are a notation for doing stuff. And we spent an hour solving the problem with regexes. And oh my God, it was such a powerful tool for this problem. And and by the end of it, they were all like, okay, we want to like deeply study regexes. And obviously that's a much less flexible and powerful tool notation than APL. But we kind of talked about how once you start understanding these notations, you can build things on top of them, and then you kind of create these abstractions. And that's, notation is how, deep human thought kind of progresses, right? In a lot of ways. So, it's like I actually spoke to a math professor friend a couple of months ago about, my renewed interest in APL. And he was like, and I kind of sent him some, I can't remember what it was, maybe doing the golden ratio or something, little snippet. And he was just like, yeah, something like that looks like Greek to me. I don't understand that. It's like, dude, you're a math professor. Like if I showed somebody who isn't in math like a page of your, research, what are they going to say? And it's interesting. I said like, there are ideas in here like Iverson brackets, for example. Have you ever heard of Iverson brackets? And he's like, well, of course I've heard of it. Like, it's a fundamental tool in math. It's like, well, that's one thing that you guys have stolen from APL. That's a powerful thing, right? It's like, fantastic. I'd never want to do without Iverson brackets. So I kind of tried to say like, okay, well, imagine like every other glyph that you don't understand here has some rich thing like Iverson brackets you could now learn about. Okay, maybe I should give it a go. I'm not sure he has. But I think that was a good example for mathematicians, is to show like here's one thing at least that found its way from APL that maybe gives you a sense that for a mathematician that there might be something in here.
On that note, because I know we are potentially, well, we've gone way over, but this has been awesome. But a question I think that might be a good question to end on is do you have any advice for folks that want to learn something, whether it's Chinese or an array language or to get through your Fast.ai course? And is there, because I think, like you said, you like to self-select for folks that are the curious types and that want to learn new things and new ways to solve things. But like, is there any way other than just being tenacious to like be tenacious? Is there tips to, approaching something with some angle? Because I think a lot of the folks maybe listening to this don't have that issue, but I definitely know a ton of people that are the kind of folks that, they'll join a study group, but then 3 weeks in, they kind of lose interest or they decide it's too much work or too difficult. As an educator, and, it seems like you operate in this space, do you have advice to tell folks,
I mean, so much, Connor. I actually kind of embedded in my courses a lot. I can give you some quick summaries, but what I will say is my friend Radek Osmowski, who's been taking my courses for like 4 years, has taken everything I've said and his experience of those things and turned it into a book. So if you, Radek Osmowski's book is called Meta Learning, Powerful Mental Models for Deep Learning. This is learning as in learning deeply. So yeah, check out his book. to get the full answer. I mean, there's a lot of things you can do to make learning easier. And a key thing I do in my courses is I always teach top down. So like often people with let's take deep learning and neural networks, they'll be like, okay, well, first I'm going to have to learn linear algebra and calculus and blah, blah, blah. And, 4 or 5 years later, they still haven't actually trained a neural network. Our approach in our course is in lesson 1, the very first thing you do in the first 15 minutes is you train a neural network. And it is more like how we learn baseball or how we learn music, like you say, okay, well, let's play baseball. You stand there, I throw this to you, you're going to hit it, you're going to run. You don't start by learning, the parabolic trajectory of a ball or the, history of the game or whatever. You just start playing. So that's, you want to be playing. And if you're doing stuff from the start that's fun and interesting and useful, then top down doesn't mean it's shallow. You can then work from there to then understand what's each line of code doing, and then how is it doing it, and then why is it doing it, and then what happens if we do it a different way, and until eventually with our Fast.ai program, you actually end up rewriting your own neural network library from scratch, which means you have to very deeply understand every single part of it. And then we start reading research papers, and then we start learning about how to implement those research papers in the library we just wrote. So yeah, I'd say go top down, make it fun, make it applied. For things like APL or Chinese, where there's just stuff you have to remember, use Anki, use repetitive spaced learning. That's been around. Ebbinghaus came up with that, I don't know, what, 150, 200 years ago. It works, everybody, if you tell them something, will forget it in a week's time. Everybody, and so you shouldn't expect to read something and remember it, because you're human and humans don't do that. So repetitive spaced learning will have you quiz you on that thing tomorrow, and then in 4 days' time, and then in 14 days' time, and then in 3 weeks' time. And if you ever forget it, it will reset that schedule, and it'll make sure it's impossible to forget it. So it's depressing to study things that then disappear. And so it's important to recognize that unless you use Anki or SuperMemo or something like that, unless you use it every day, it will disappear. But if you do use repetitive spaced learning, it's guaranteed not to. And I told this to my daughter a couple of years ago. I said, what if I told you there was a way you can guarantee to never ever forget something you want to know? She was like, that's impossible. Is this like some kind of magic? It's like, no, it's not magic. And I sat down and I drew out the Ebbinghaus forgetting curves and explained how it works. And I explained how, if you get quizzed on it in these schedules, it flattens out. And she was just like, and I was just like, what do you think? I was like, I want to use that. So she's been using Anki ever since. So maybe those are just 2. Let's just start with those 2. Yeah. So go top down and use Anki. I think could make your learning process much more fulfilling, because you'll be doing stuff with what you're learning and you'll be remembering it.
Well, that is awesome. And yeah, definitely we'll leave links to not just Anki and the book Meta Learning, but everything that we've discussed throughout this conversation, because I think there's a ton of really, really awesome advice, and obviously to your Fast.ai course in the library. And we'll also link to, I know you've been on, like we mentioned before, a ton of other podcasts and talks. So if you'd like to hear more from Jeremy, there's a ton of resources online. Hopefully, it sounds like you're going to be, building some learning materials over the next however many months or years. And so in the future, if you'd love to come back and update us on your journey with the array languages, that would be super fun for us, because I've thoroughly enjoyed this conversation.
Thanks, Connor.
And thank you so much for waking up early, all on the other way side of the world from us, at least in Australia.
Thanks for having me.
Yeah, I guess with that, we'll say happy array programming.
Happy
array programming.